Hello and welcome to NASA headquarters. My name is Dwayne Brown with the Office of Communications, your host for today's program. During the next hour, we'll take you on NASA's upcoming epic trek back to Mars. On November 26th, NASA's Mars InSight lander will touch down on the red planet, becoming the first ever mission to study the heart of Mars. Mars has a heart, you ask? Well, stay with us to get a better understanding of that and much more. Today's show will feature talks from mission engineers, scientists. They'll also take your questions here from our audience in Washington, our phone lines across the nation, and of course, social media using the hashtag AskNASA. I have my Red Planet red tie on. Are you ready? Let's go to Mars. First up, to tell you about the spacecraft and how we will land on the Martian surface is Tom Hoffman, InSight Project Manager from the Jet Propulsion Laboratory in Pasadena. Tom.
Thank you, Dwayne. I can't express to you the excitement that I have to stand up here in front of you today, less than a month to landing. I've been working on this project for more than 7 years, and to get to this point, we're on the precipice of landing on Mars. Going to get back some groundbreaking science is absolutely a tremendous feeling to me. Many of the team members that you're going to hear about today have been working on this even longer than I have, so I know they're equally, if not more, excited than I am to tell you about this great mission. So first off, our trip to Mars started May 5th of this year from Vandenberg Air Force Base. It was the very first interplanetary launch from Vandenberg Air Force Base. Being a native Californian, it was great for me to be able to break the monopoly that the East Coast has had on interplanetary launches. And so we launched on an Atlas V rocket. And what we were expecting to see was something really cool like this, which is an Atlas V launching from Cape Canaveral that carried both us and the Marco spacecraft. That's not exactly what we saw. Anybody that's familiar with Central Coast of California in the summertime knows sometimes it can be just a little bit foggy. And so if you're really, really close to the rocket, you might have seen something like this. It's a lot of glow and a lot of fog and not too much excitement for the people that were actually there witnessing the launch in Lompoc Air Force Base, or Vandenberg Air Force Base in Lompoc. But people that were just a little bit above the clouds saw some spectacular sights, whether they're on a mountaintop or whether they're in a private plane. Looking at that rocket come out, it was a beautiful sight. And fortunately for anybody who was south of Lompoc area, either Santa Barbara, Los Angeles, even all the way to San Diego, saw this beautiful streak through the air at about 4:05 a.m. on the 5th of May. So what have we been doing since we've launched? We've been in what we call our cruise phase. So we've been doing engineering checkouts, science checkouts of the different instruments before we get to Mars to make sure we're completely ready once we get there. And so we launched, as I said, on the 5th of May. So we've been on a ballistic direct trajectory to Mars. We've been getting closer every day. And right now, on Halloween Day, we're very, very close to Mars, catching up. When we do enter the atmosphere, we're going to be going at about 12,300 miles per hour. And in just 6.5 minutes, we're going to get down to 5 miles per hour just before we land. And I'm going to explain to you exactly how we do that. It's a very interesting concept. So we start out with our cruise stage, which has been giving us our power and our communications since we launched. As soon as we get to the atmosphere, we get rid of that cruise stage. So this is what it looks like. So our cruise stage is there at the back end. We let that go. We have the aeroshell, which contains our lander in it. It hits the atmosphere, starts heating up. You can see it gets very, very hot. That's slowing it down most of the speed. So it gets to about 850 miles per hour. When we pop this parachute, the parachute takes us down close to the ground. We get rid of our heat shield that's been protecting us in the atmosphere. And then we start acquiring the ground with our radar from the lander. That tells us what our elevation is and lets us know when it's time to let go. We free fall, which is absolutely terrifying for me as a project manager to know my spacecraft's falling to the ground. But we do start firing rockets, and we slow down to about 5 miles per hour by the time we actually get down to the surface. Right when we get there, we'll go ahead and turn off those retro rockets, let the dust settle literally. You can see it's kicking up a fair amount of dust. And then we have one more important step, which is to unfurl our solar arrays. Since we're the very first lander on Mars to last for an entire Martian year, so 26 Earth months, not moving and just using solar power, it's important for us to get those solar rays out. And so that completes what we call our entry, descent, and landing phase, and now we're ready to start doing the science. But you might wonder, how did we choose this particular landing site? Why did we choose that? So I have a video to show you. Dr. Thomas Zurbuchen, the head of the Science Mission Directorate, and Ramon DePaula, who's our program executive here at NASA headquarters, are going to explain that to you.
Have you ever wondered how NASA decides where to land spacecraft on other planets? Hey, welcome to Science in Seconds. We're going to tell you how we selected Elysium Planitia as the Martian home for NASA's InSight lander.
InSight's purpose is to study the interior of Mars, not the surface. In the selection of a landing site, what's on the surface matters less on this mission than for previous missions.
Planitia is Latin for a flat surface. Elysium is from the ancient Greek name for an afterlife paradise.
InSight's scientific success and safe landing depends on landing in a relatively flat area, similar to a parking lot, where rocks are few in number. InSight requires a landing site that must be close to the equator to ensure the lander's solar arrays can provide power throughout the year. The chosen flat surface is perfect for InSight to study the interior of the red planet.
We're on our way, Elysium Planitia.
All right, so that's how we've chosen that particular location on Mars and why we chose that particular location. One of the very first things that we're going to do when we land is we're going to take a picture of what it is our landing area looks like, because we have to go through something we call instrument deployment. You're going to hear more about that later from some of the other speakers, but just getting to the surface of Mars and getting our solar rays unfurled is not enough. We actually have to take the instruments off the deck and put them onto the Martian surface. So that's why we're hoping that we see a picture kind of like this, which is a really flat-looking area, much like a giant Walmart parking lot, hopefully with not very many rocks in the area. This is a little bit rockier than I'd like to see. So hopefully it's really not really a safe area to place our instruments. One of the other things that's really interesting about this mission is it's not just one spacecraft going to Mars. It's not just InSight. We actually have two tag-alongs that flew with us on the Atlas V and have been tracking us ever since, called MARCO. So that stands for Mars Cube 1. So we have two of them, MARCO A and MARCO B. They're about the size of a briefcase, so they're not very big spacecraft at all, but their main purpose is to do a technology demonstration showing that we can put CubeSats into interstellar space. They've been successful in doing that. But we're really, really hoping that one of the other things they're going to be able to do is give us communications while we're doing our entry, descent, and landing phase. Oftentimes we've had other assets that have been able to do real-time information for that phase, but this time we don't have those assets in the right position. So we brought along our own relay assets, and they kind of look like this. There's two of them. This is the UHF antenna at the bottom. They have an X-band that'll be talking back to Earth for us. They'll fly in formation, trailing behind us, waiting for us to start giving them a UHF signal through here, and then they'll be broadcasting that back to Earth so we know what's exactly happening each step of the entry, descent, and landing process. All those steps that I showed you a little bit earlier in the video. So this is what it looks like when we get there. So the two MARCOs are on either side of InSight as it's entering. We have MRO, or Mars Reconnaissance Orbiter, that will also be collecting the data, but it can't send back the data real time. Only the MARCOs can do that real time. So we're really hoping that they work out as a technology demonstration. The MRO will be collecting that data, and about 3 hours after we land, we'll be sending that back to the Earth, just in case the MARCOs don't work. We'll still get all the information about the entry, descent, and landing. So that's basically how EDL works, how EDL communication works. To tell you more about how InSight fits into the overall portfolio of the Planetary Science Directorate is the head of Planetary Science Directorate, Lori Glazed.
Great. Thanks so much, Tom, for giving such a great description of what the InSight mission looks like and how it's going to enter the atmosphere and descend down through the atmosphere and land on the surface. So this incredible spacecraft, you've heard the phrase, the saying, it takes a village. Well, this spacecraft didn't just take a village, it took almost the entire planet to pull this mission together. Multiple international partnerships between international space agencies came together with contributions from France, from Germany, from England, from Poland and Switzerland and Spain. Contributions from all of those countries came together with the United States and with NASA to put together an incredible scientific payload that's going to be able to measure the heartbeat and actually understand Mars from the inside out. This is an incredible feat and really just a tremendous, tremendous mission. This graphic here shows the entire planetary fleet, and down here in the bottom right-hand corner is the missions that we currently have at Mars, including InSight. These missions are either in development, all of the missions are either in development or in operations. And all of these missions are, not all of them, but they're all trying to address fundamental questions that we have about how our solar system formed and evolved. Where did it come from and how did we get to where we are today? For an example, I wanted to show you we have a couple of missions on here. OSIRIS-REx over here to your left is a mission that's going to rendezvous with the asteroid, near-Earth asteroid Bennu, coming up in early December. It's going to map out that asteroid, and then after a while it's going to take a sample from the surface of the asteroid and bring that sample back to Earth, where we're able to analyze that sample, understand its chemistry, help us to understand the chemical composition of these near-Earth asteroids that are building blocks for the elements of our solar system, all of the planets. Another good example of how we address that question of the formation and evolution of the solar system is the New Horizons mission, which is going to fly by a Kuiper Belt object on January 1st, on New Year's Day. The Kuiper Belt is out beyond Pluto. It's very far away, and it's made up of these primordial objects that we think are remnants left over from the early formation of the solar system. And when New Horizons flies by that Kuiper Belt object, MU69, on January 1st, that'll be the first ever time we've gotten a close-up view of one of those early objects. So these missions and many of the other missions in our planetary portfolio are trying to address that question of how did the solar system form and evolve in different ways, just as InSight is going to try and understand how the rocky bodies in our solar system formed and evolved over time. I also wanted to mention that NASA's exploration campaign, exploration program that we're undergoing now is an effort to try and return to the moon with scientific experiments and technology demonstrations to help us prepare to send humans back to the moon and eventually on to Mars. What's interesting to me is that the scientific experiments that are going to be done with the InSight mission have actually already been done at the moon several decades ago as part of the Apollo program. And so with that, I'd like to introduce Dr. Bruce Bannert, who's the principal investigator for the InSight mission. And he's going to talk to you much more detail about the science experiments that are going to be conducted on InSight and a little bit of information on how they relate to what's been done on the moon previously. Thank you.
Thank you, Lori. So I am stupendously excited to be up here today. I've been dreaming about this mission, this science, for about almost 40 years and actively scheming towards it for at least 25. And so to get to this point where we're less than a month away from landing on Mars and actually doing this science is just a real treat for me. So I'm going to talk a little bit about the science, but first, I have a little a clip here of Dave Scott, who was the astronaut on Apollo 15. This is him getting out of the Apollo 15 capsule. And Lori mentioned how we've been to the moon, we're going to Mars, and we're going to the moon as well with NASA. And this actually has a pretty direct connection to InSight, and I'll return to that in a few minutes. So what is it that we're doing with InSight? InSight is going to explore the deep interior of Mars, from the crust all the way down to the center of the planet, to its core. It's really the first mission to go and look deeply into the insides of a rocky planet other than the Earth-Moon system. And we're going to Mars specifically to look back into the origin of the planets of the solar system. So in this graphic, you can see over on the left we have the Earth, and the Mars in the middle, Moon on the right. And in order to investigate, what's going on inside the planets and how that relates to early solar system formation. Why are we going to Mars? We're on the Earth. It's a lot easier to get to. It's a lot easier to study. And we absolutely understand a lot about the interior of the Earth and gotten a lot of information for it. But if you really want to know about the very beginning of the planets, sort of the birth of the planets, what happens to them just in the few first tens of millions of years after their formation, Earth is not really a very good laboratory because Earth has been extremely active. It's a big planet, holds a lot of heat, a lot of energy, and has been very geologically active over its entire history. And so most of the record of the early processes that formed the Earth have been erased either by plate tectonics, by vigorous mantle convection, and so forth. And so we'd like to have a planet that's just a little bit calmer and that can retain that evidence. The moon is actually pretty great that way. It's a small planet. It cooled very quickly, and it does actually retain a lot of the evidence from its early formation. But the problem is it's so small that the conditions inside, the pressure and temperature, never get to the levels that are characteristic of the bulk of the inside of the larger rocky planets. And so Mars is kind of in the sweet spot. It's big enough to have experienced all the processes that we're interested in, but small enough that it hasn't been so vigorous that it's erased it all. So it's kind of, we like to call it the Goldilocks planet. It's just right for investigating the early solar system. And so how do we do that? How do you look deep inside a planet? Well, the best way to do it is by using seismology. And seismology uses what are called seismic waves, which are basically just vibrations, shaking of the planet, to probe deep into the planet. So those waves propagate through the planet, and as they propagate, you can see that they get bent, they go in different directions, it affects the wavelengths, it affects the amplitudes, and then when we measure those amplitudes, measure those vibrations at the surface, we have techniques that we can use to sort of unravel the entire pathway through the planet and figure out what kind of materials that they pass through, what kind of interfaces that they may have bounced off of, and then we can use that information to understand the size, the composition, and the configuration of all the layers of the inside of the planet, particularly the core, the mantle, and the crust. And these parameters, these divisions and compositions are all very closely tied to how that planet formed very early on. We start out with a cloud of material that's orbiting around the sun in the very early solar system that condenses into planets through gravitational attraction, but they move from a uniform ball of material that's kind of made up of the same kind of rocks as meteorites, which is pretty uniform material, and then they transform like a caterpillar in a chrysalis. They transform from a featureless ball into the diverse and complex planets that we see today. And that's the process called differentiation that we really want to key into with this mission. In order to do this, we need to be able to get our instruments onto the surface of the planet. Now, for Apollo, we actually had a very convenient deployment system. It's called a human being. This is Buzz Aldrin on Apollo 11 deploying the very first seismometer that was operated off of the Earth back in 1969. This is the seismometer down here that he's just carried from the lunar excursion module and placed onto the surface at a decent distance away from the spacecraft. This had its own power supply with it and its own communication system, and this was sort of the beginning of our exploration of the deep interior planets other than the Earth. Similarly, we put a heat flow probe onto the moon, actually several of them. This is Dave Scott from Apollo 15, a little bit after he made that trip down the ladder that I showed you earlier. And here he is drilling down into the planet. So in order to measure the heat flow coming out of a planet, you have to measure the temperature not only at the surface, but down at depth as well, so you can find out how much of that heat is escaping from deep inside the planet. And you can see that he's leaning on that thing, he's pushing it down. It's not really easy to dig into or to drill into rock or even into soil. And so this is a fairly difficult process. We don't have astronauts on InSight, you may have noticed. So we have to get a little bit more clever about how to do that. And our next couple of speakers are going to talk a little bit more about the deployment process, how we robotically sort of mimic the kinds of things that we were doing with astronauts back in the 60s and 70s. And so with that, I think this is my final slide. I'd like to go on to pass this on to our next speaker, which is Sue Smrekar. She's the deputy principal investigator for InSight, and she's going to talk a little bit more about the instruments and the deployment system that we're going to be using.
All right, thanks, Bruce. So we're going to talk a little bit about how InSight actually accomplishes this amazing science. And you saw in Bruce's presentation how seismic waves travel through the interior of the planet. When they encounter those waves, those layers, the seismic waves can speed up or slow down depending on the density of the material, and they create multiple waves. So what I'm going to show you here is a seismic event happening near the surface, and it's going to interact with these layers near the surface, and I'll show you what it actually looks like at our lander. So here the seismic wave is interacting with those layers near the surface. At the top, you're seeing what the seismometer records. So this is, we've been talking about the pulse of Mars, the heartbeat, and this is what our seismometer is actually going to record. You're seeing two different waves there. You're seeing the vertical displacement of the ground, and you're also seeing the horizontal displacement of the ground. So here we've shown what two seismometers would record. We on InSight actually have 6 seismometers inside that small package that we place on the surface. And we do that so that we can not only record the full spectrum of a seismic wave, but also to tell what direction it's coming from. So the shape of these waves, their amplitude, their spacing, it tells us all about the path that they've traveled to actually get to our seismometer. And that gives us the ability to discern what the layers are inside the planet. Okay, so as you know, we have also a heat flow and physical properties package, the HP cubed, and we don't have the benefit of the astronaut to drill a hole for us. So the HP cubed actually has to hammer itself under the ground. And what you're seeing here, it's basically a nail that contains its own hammer. A motor compresses a spring. That spring is released, and it accelerates that mass downward, which acts like a hammer on top of this cylinder, which we call a mole. The mole goes down a couple of feet into the ground, and it sends out a pulse of heat. What it is doing there is measuring the thermal properties of the soil. When it sends out that pulse, we determine how long it takes for it to cool off again, and that tells us whether the soil is insulating or conducting. We go down all the way to the end of the tether. And my family likes to tell me I'm short, and so it looks like it's kind of a short tether compared to me. But in fact, what we want to do is get down to about 10 to 16 feet. All along this tether, there is a string of 10 temperature sensors. And what we're going to do is determine how fast the temperature increases with depth. That tells us about the heat coming out of the planet, that energy that's available for driving geologic activity. So we want to go down 10 to 16 feet because at the surface, there's a lot of temperature variation going on. There's a daily temperature variation. There's a seasonal temperature variation. Even our lander causes variations in the temperature. So we want to get down to 10 to 16 feet because when we get down that deep, we get away from all the temperature variations near the surface. So that's why we're trying to deploy it down all the way to this full extent. Okay, so as you know, before we can start working with our instruments, we have to be able to deploy them onto the surface. And this is an animation of our robotic arm picking up the seismometer, or the 6 seismometers inside this package, and placing it on the surface of Mars. In this video, it takes about 20 seconds for this to occur. On Mars, it's going to take about 2 or 3 months before we actually have our seismometer on the ground. The reason for that is that we're going to take all of the data that we possibly can to choose an optimal place before we put our instruments down. So as soon as we get on the surface, we're going to start taking image data to look for the rock distribution. We're going to take stereo images that help us determine how big are those rocks. if there are any slopes within the reach of the arm. We're also going to take temperature data of the surface. That temperature data helps us determine what the particle sizes are on the surface, and that can give us information about whether we think the instruments might settle at all after we place them on the surface. So we want to take all the data, assimilate that, and try to choose the best location to put our instruments down. So that's going to take us, we're going to take our time and do that to the best of our ability. Okay, so you've seen what it looks like in the animation. I'd like to next go to JPL, introduce you to our lead deployment engineer, Jamie Singer. And she is going to tell us, where are you standing right now?
Hi, Sue. I'm at the Jet Propulsion Laboratory in situ instrument laboratory, which we call ISL for short. This is the space where for many years now, engineers like myself have been practicing and preparing to do the instrument deployment with our test bed. So that's what you see right here behind me. This is the deployment test bed. It is like a stunt double. It contains a lot of the similar hardware to the flight lander. So you know the flight one is on its way to Mars right now. This one has the instrument deployment arm, which you can see right here, as well as a sandbox area that allows us to practice deploying models of the instruments.
Cool. So once we actually land on Mars, can you tell us about what you and your team are going to do to actually get ready to put our instruments on the ground?
Yeah, sure. That's a great question. So within the first week or so on Mars, we're going to be taking images with the 2 cameras that we have. I'll actually take a moment to point those out now. So we've got 2 cameras. One here is on the robotic arm. This is the instrument deployment camera. And the second camera is the instrument context camera, which will take the first image that we see of the InSight's landing spot after InSight lands. So once we have the detailed images from the camera that's on the arm of the entire workspace, that's that work area right here in front of the lander that's reachable with the robotic arm, the engineers and scientists will evaluate the data and find kind of the second landing site for the instruments, which is the place that we're going to deploy them with the robotic arm. In parallel, right here in ISL, in the test bed, we're going to also do what we've been calling Mars forming, which is we're going to create this work area to look like the surface we see on Mars. So we've got our shovels and our rakes and some rocks all prepared to kind of Mars form and make this sandbox look like the surface of Mars that we see, and do a final deployment test of the instruments.
Cool. So I hope you don't have to pull out any of the really big, heavy rocks to put out there. But so maybe could you show us a little bit more of what's you have set up in the lab today?
Yeah, sure. So as you just showed the video of the seismometer being deployed, I'll show you that that's the configuration that things are in right now. So we have here actually the wind and thermal shield that will be deployed on top of the seismometer. So I'll lift this up. What this does is it keeps the seismometer from getting too cold at night. It also protects it from the wind measurements. Legs are supposed to fold down. The wind measurements that could affect the seismic data. So this is the seismometer itself, containing the 6 seismometers or sensors that you talked about earlier. And it's tethered here with cabling. So we call this the tether. It's cabling that connects the seismometer to the lander, which allows the lander to provide power to the seismometer and allows the seismometer to send data back to the lander. So the other instrument, the heat flow probe, is still up here on the deck. This is where it will be when it's land before it's deployed. So you can see it back here. Here's the heat flow probe, HP cubed. Okay, and then, yeah, I've already pointed out, again, the 2 cameras that are right here. And this is the grapple that we have at the end of the robotic arm. This has got 5 fingers, which connect to a hook on top of each of the instruments. And that's what enables us to deploy them with the robotic arm.
All right, awesome. Thank you so much, Jamie. All right. So I can't wait to see the I can't wait to see the images of the surface of Mars and to let Jamie and her team get into action. So thank you so much, and back to you, Dwayne.
Let's give our presenters a nice round of applause. See, not only can we go to Mars, but we can give a high five 3,000 miles away. So we like to have fun, scientists. Now, we're going to transition into our Q&A, but I got to ask, because I believe folks are, you know, it looks like our young scientist was tethered also. What does that mean that she's tethered to the lander there?
Are we going to let her answer?
Yeah.
Yeah.
Okay.
Jamie.
Yeah, is that a question for me? Okay, so I think you're talking about this tether right here, which is a bracelet that I've got to wear in contact with my skin and connects me here to the lander. So I think that we've all kind of felt like if we slide down a slide at the playground or like walk across a carpet and touch a light switch or something, there's a little sparkle discharge of that charge if it builds up in those types of environments. Well, we don't ever want that to happen here with the hardware because that could damage the hardware. And so this smock as well as this wrist strap kind of prevent that from happening.
Okay, thank you. Okay, so here's what we're going to do. We're going to transition here, starting with questions in Washington, then we're going to go to the phone lines, and then, of course, we're going to go to social media. Send those questions in. There's a lot of excitement on social media. Hashtag AskNASA. A shout out, we have students here from our local university, and we're going to give them an opportunity. They have their laptops, and they're covering the story. So we're going to give you a chance to ask a question, and we were talking. You just raise your hand, wait for the microphone, and here, we've got somebody behind you. Let's do that. Wait for the microphone. Please give your name and affiliation if you can, and then we'll take a few questions here, stand up, and then we'll go to the phone lines and then social media. We'll see what. Yes, sir. Name and affiliation.
Ivan Coran of Agence France Presse. Do you know if there could be a dust storm or strong winds, and how much would it affect the descent? And can you postpone the landing if anything happens?
I'll answer that question. We're going to land on November 26th at about 11:47 Pacific time, regardless of anything. That is, we're on a ballistic entry and we can't change it. We can't make any changes. We can't go back around again. So we know we're gonna land there. But we did know from the very beginning, the outset of this project, that we were landing during what is considered global dust storm season on Mars. So we knew that was a possibility. And so we've actually designed our entry, descent, and landing system to accommodate for that. So we've increased the thickness of our thermal protection system, the part that you saw getting very hot in the video. So we've taken that into account, and we'll be looking as we get closer to Mars. We actually have Mars weathermen, which I hope are better than Earth weathermen, but they're going to be trying to predict what it looks like on Mars on the day that we're going to land, and we'll make fine-tuning adjustments based on what we see there.
Please stand up. Name and affiliation, please.
Good afternoon. This is Tom Risen with Aerospace America. Thanks again. I'm excited about the landing. When it does arrive on the 26th, what kind of images will people be able to see first? I know it's going to take a while to get everything going, but will there be a live stream when you're on the surface? Will there be photos from orbit? And you said there'll be one when you get on the surface, but will there be anything from orbit or what will people be able to see first, the first couple days that the landing happens?
Yeah, so the very first image that we're going to get back might be very cloudy and not particularly good because we're going to take it right after we land. And remember, we saw all that dust being kicked up. That'll be from the under-deck camera that Jamie pointed out that gives us a fisheye view of the entire landing space. If we're lucky, we might get a good picture, but it's likely because the cover will still be on that it'll be a little bit hazy. We're going to throw the cover off later and take some pictures on the next day that hopefully we'll get back. But we have to kind of wait for literally for the dust to settle before we start taking a bunch of pictures. And then we want to make sure that we're really in a good power state, which is going to take us about another day before we start doing a bunch of imaging. But because we're a stationary lander, once we start taking images, we're not going to be, every day a new image. It's going to be kind of the same image because we're in the same area for the duration, which is what we need for the science we're doing. No. No, we might try. The question is, are we going to get any shots on orbit? We will make an attempt, as we've done in the past, to get a picture of us on the parachute, but that's always a very dicey chance. We've been very lucky in the past of getting those, but we'll have to see if that works out again from Mars Reconnaissance Orbiter. But we don't have any descent imaging on the spacecraft itself.
Okay, thank you. So we're gonna come back we're gonna go to the phone lines next, and I believe we have Leo Enright from Irish TV. Long time, Leo. Hope all is well.
Hi, Dwayne. Good to talk to you. I had a question about. There was a lot of talk about Apollo, but of course the first seismometers designed for the moon were Ranger seismometers. We won't go there in terms of what they achieved, but am I correct in understanding that they're the legacy for the seismometers that are now used in schools in the United States, in Ireland, in France, the whole school network, and how does that tie in with what this mission is doing in terms of not just public outreach per se, but education?
That's a great question. We're taking advantage of several programs around the world called, in the United States it's called seismometers in the schools. In France it's seismos en école, and similar programs in Germany and Switzerland, which are actually set up for looking at terrestrial, Earth-based earthquakes, and showing students, how earthquakes are sensed with the seismometers and what kinds of analysis you can do. And we're plugging into that program, and we're going to be supplying the seismic data coming down from Mars directly to those programs in the schools around the world. And in some cases, I think the students might actually be getting the data before our scientists do. And they've told us they promise not to publish before we do. But so they'll be getting Mars data. They'll be able to put it next to the Earth data. They'll be able to analyze the arrival times and things like that of the marsquakes, just like the scientists on the teams are going to be doing. And so we have a lot of excitement around that, and I think there's a lot of students that are really raring to go on that program.
Okay, we're going to take one more question from the phone, and then we're going to go to social media. Again, send in your questions, #AskNASA. I believe we have space.com on the phone.
Hi, this is Sarah Lewin from space.com. I was curious, which of InSight's early operations after landing will make you the most nervous as it's happening?
Yeah. Well, after landing, I'm going to be very, very happy after we get a safe landing. But really, I'm going to be nervous until we get that first really good image back of what our workspace, the area in front of the lander, is going to show us. We're hoping that it's really flat. Literally a parking lot is what we're wanting. But if there's rocks in there and there's slopes in there, then Jamie and the rest of the deployment team is really going to have a job in front of them. Luckily, our lander, there's nothing that's real time critical for us to get stuff done right away after we land. But if we do encounter a difficult workspace, it's going to take us a little bit longer than we would like to finish that deployment operation. And Jamie will be much busier than she would like to be.
Okay. Now, we go from the phone lines into social media, and I want to welcome to our social media team and helping out today, Joanna Wendell. Joanna, social media is a buzz, right? We got some questions?
Oh yeah, there's tons of questions. So let's see, first one from Andrew on YouTube asks, can InSight detect impacts and landslides? What other science will InSight give us besides core and mantle activity?
We'll be able to, as you said, we'll be able to see marsquakes. We'll be able to see impacts with a seismometer. We're pretty far away from any mountains or cliffs, so we probably won't be able to see landslides, although seismically you can see landslides. It's possible that we could actually see some vibrational activity, quake activity from looking at the motion of magma in the crust from active volcanic activity. As well as doing the seismic measurements, we're measuring the heat flow from the planet, seeing how much energy is coming up from deep in the planet, which is sort of the driving force behind most geologic activity on a planet. And then we also have a very capable weather station on InSight. We're measuring the pressure, the barometric pressure. We're measuring winds. We're measuring the atmospheric temperature, and we're measuring actually the ground temperature on a continuous basis around the clock. And so we'll have the best weather record of any place on Mars when we're done with this mission. And I think we're still, still thinking about all the different things that we can do with the instruments we have, and once we get on Mars, we'll think of even more things, because this is an extremely capable, extremely flexible payload that we're sending to Mars.
Great. So a question from Facebook. How can you figure out the interior of Mars with only one seismometer? I thought it requires at least 2.
That's a great question. That's a question that I've been asking myself, and people have been asking me for decades. And of course, on the Earth, you usually like to have at least 3 or 4 seismometers, so you can triangulate on the earthquake and figure out how far away it is. Once you know how far away it is, you know how long it took you to get there. Then you know what the velocity is. The velocity of the waves, the speed at which it goes, depends on the material, and so that's where you start getting all the science out of it. If you only have one station, you have to get a little bit more clever. And actually, we're going back to some of the technology and techniques that were used around the turn of the 20th century, 100 years ago, when the first seismology was being developed in the early 1900s. And you can actually figure out how far away it is from a couple of different methods, usually by the spacing of different wave arrivals. You have P waves, S waves, surface waves. By putting those things together, you can figure out how far away it is, and we're able to use something called polarimetry, looking at the actual direction that the waves are vibrating. We can actually use that to trace back to the direction and figure out where where the Marsquake occurred. And we've been simulating that with Earth data, with single seismometers on the Earth, pretending like we don't have that information. And we've been able to show that these techniques are working really well and can get us those locations and get us those seismic velocities and timings at an accuracy that's good enough to make the measurements and the determinations we want to make in terms of the compositions and depths.
All right, I've got one more question from Facebook. Hey scientists, what if there are no Marsquakes? What happens then?
Why don't you take that one?
Okay. Well, we, as Bruce was talking about, we do have other instruments. We are certainly going to learn about the heat flow coming out of the interior, and we actually still are able to measure the size of the core, because one of the experiments we didn't take time to talk about today is called the RISE experiment, and what it does is use 2 small low-gain antennas on either side of the lander. And that, what we do is track the position of the lander very precisely over the course of a Mars year. Now, of course, what we're really doing is not tracking the position of the lander, which is not going anywhere, but we are monitoring the wobble of Mars. And the classic example is if you take a hard-boiled egg and a raw egg, put them on a table, and you spin them, they wobble differently, right? And so basically by using the very minor, very small wobble of Mars as it goes around on its axis and goes around in its orbit, we're actually able to derive both the size of the core from that information, as well as whether it's liquid or solid. So we get that information about the core, we get information about heat flow, and if we and further, it's extremely unlikely that we will see no Marsquakes, because we know the rate of impacts hitting the surface of Mars. So we have calculated how many we expect to hit that we can detect. So that's pretty much an assured source, and we do certainly expect Marsquakes. So we'll get we expect to get them, but we would get some science as well, even if there are none.
Okay, before we come back here, we're going to send out a question to JPL. Actually, it's a couple of questions. The first is, what is the team doing now? What will we be doing leading up to landing? And the primary mission, can you explain how that's going to work? How long will that primary mission be for JPL?
Okay. So let's see, what we're doing right now, so for the surface team, the team that works on the deployment, like myself, is actually, we've finished all the testing that we have to do before landing, and now we're starting to plan the first few sols that we're going to have on Mars in a really detailed way. So we're planning those initial sols and making sure everything is completely ready to go on those activities that we're going to do on the first few sols, like unstowing the robotic arm, acquiring the images of the workspace, that type of thing. So that's what we're doing right now on the surface team. Of course, the cruise and EDL team are preparing for the landing. As you know, we had our last final rehearsal of that last week. So then I think the question is about the prime mission, and I'm not sure if that was about actually deployment or the entire 2 years of the science monitoring. So I'll talk a little bit about deployment, and then I might ask Bruce to talk about the science monitoring part, if that's what the question was about. So the deployment phase will take 2 to 3 months, which I think Sue touched on a little bit. So it's going to take us a couple weeks to acquire the images in detail of the workspace and do the testing and get ready to deploy the seismometer. Once we deploy the seismometer, it's got some activities that it needs to do. It's got to level itself. It recenters the sensors inside the sensor assembly, so it can get good seismic data. We've got to release more tether out of the tether box. There's a lot of activities in there with the ground, the operations team checking in kind of along the way every day, because we're only going to do this deployment once, and so we want to do it correctly. Then we'll deploy the wind and thermal shield. That may be after maybe 1 to 2 months after we've been on Mars, and then the heat flow probe will be deployed next, and then we'll release the mole. And that's the end of the instrument deployment phase. And then it's ready for the science team to really take over and start taking their science observations and get great science, which will go on for at least 2 Earth years, which is 1 Mars year, about.
Oh, thank you so much. Okay, so we're gonna, before we come back here, Social is really, really excited about this. We're gonna take one more question, then come back here, and then we're gonna wrap it up. So go ahead, Joanna.
So from Twitter, we have a question. How does the robotic arm work?
JPL.
Okay, so let me maybe show you guys a little bit more detail about the robotic arm. So the robotic arm has 3 joints that we use to do the instrument deployment. So we'll look first here. This is the shoulder, which has an azimuth and an elevation. So azimuth allows the arm to kind of move from side to side here. And then elevation brings this whole upper arm up and down. Then we also have the elbow joint here, which changes the angle between the forearm and the upper arm, just like our elbow. And then we have the grapple, which is down here. So it's got 5 fingers that open when the wax actuator in here heats up. So that's what controls this. So when we heat it up, these fingers open, and then when it cools off, and there's a little spring in there that helps close it and keep it securely around the grapple hook on the instruments. And so this is controlled by software that's also running on the computer in the spacecraft. And we also have operators here on the ground that write the commands every day of how exactly to operate the arm. So it may be on the level of, when we do the deployment, it's one sequence, and there'll be, several different moves that the operators are determining here on the ground and simulating.
Thank you so much. Okay, so before we wrap up, we're going to take one more question coming back here to Washington. Wait for the microphone and your name and affiliation, please.
Aloha, my name is Pascal Creed-Pinner. I'm an Albert Einstein Fellow, and I'm here with some fellow fellows. We're all educators, so my question is about students. How are we going to engage our students, both with the deployment phase, the landing, all of that, and then with the ensuing science over the next 2 years? What kind of things are you going to have for our kids?
Well, as I already talked about, the seismology in the schools project that we're working on to get the seismic data out to the students. We're also, we have a lot of interns that come into JPL and actually get incorporated into our daily operations and trying to get students come in and see what we do, help us to take care of some of the jobs that we have. We have a lot of material that we're preparing that'll be available both online and that we'll be pushing out to the schools that sort of relates the kinds of questions that we're asking and the data that we're getting to earth science and to the processes on the earth, and really we want to bring all this stuff back to what does it mean about our planet, what does it mean about why the earth is the way it is today, where we've come from basically in some sense, and that connection I think at a level that is accessible and exciting to kids, I think is one of the most important things that we're going to be doing on this mission.
Well, thanks to the Mars InSight team for today's program. We're going to wrap it up here. The Mars InSight lander touching down on the red planet November 26th. Now, studying the red planet as never before. It's not just a mission to Mars. Learning how other rocky worlds, including Earth and the Moon, will form. Better understanding our solar system, even aiding in the search for Earth-like exoplanets, and perhaps, just perhaps, which ones might be able to support life. And of course, for more information and landing updates on the website, visit www.nasa.gov/insight. And we know we have lots of questions as we lead up to the landing. The press kit, the InSight landing press kit. It is a magnificent document that pretty much can answer any question from A to Z. Online at http://go.nasa.gov/insight_PK. And I hope I got that right, so it's up on the screen here. And keep those questions coming at #AskNASA. Again, mark your calendars. November 26th, humanity is going back to Mars. And to our JPL colleagues, a message to you from Washington: go InSight. Thanks for joining us.